Stealing saved passwords. As security experts, we often recommend users use a password manager to store their passwords. However, some password managers will conveniently autofill any login prompt as soon as it's displayed on screen. We can take advantage of this to steal the credentials a user has stored in their password manager. In most situations, this can be done almost instantly and inconspicuously. Not all password managers will autofill login prompts, but many of the built-in browser password managers will, like the ones found in Chrome. Typically, they search for the combination of a username or email input and an input that has the type attribute set to password. As attackers, we could create a similar form for a browser to autofill, which allows us to steal the credentials and exfiltrate them out. While we could add the HTML input tags in the script payload, we'll keep everything in the XSS file instead to stay organized. In this file, we'll have to create a username and password input. Once the inputs are added to the page, the password manager would automatically fill them with the saved credentials. After some time, we'll send the value of the input back to our Kali machine. We'll first save the body of the document into a body variable on line 1. On lines 3 and 8, we'll create two elements, U for username and P for password. The username input element will have the type attribute set to text, and the password input element will have the type attribute set to password. Found on lines 5 and 10, the input fields will have a fixed position, so they don't interfere with the application. At the end, we'll set the opacity of the input fields to 0 so they aren't visible. However, we'll comment this out for now so that we can examine the input boxes in the victim's browser and then append them to the body once they're created. At this point, the browser should fill any saved credentials. To confirm, we'll set a timeout for 5 seconds on lines 16 through 18, at which point a GET request will be made containing the value of the username and password. Once the file is saved and the HTTP server is running, we'll instruct the sandbox to render the exploit with used stored password checked. The credentials are automatically filled in at the top left. If we wait 5 seconds, we should also find the credentials sent to us in our HTTP log. Excellent. If we uncomment the opacity, we find that we still get the credentials, but the user can't observe the input boxes on the page. Additional improvements can also be made here. For example, instead of immediately retrieving the value, we can add a change event listener on the input box so data is only sent when the value changes. This would allow us to capture the credentials even if the password manager had a delay. However, in this situation, it's unnecessary. Phishing users. Given that we have full access to the HTML document, we could also rewrite the entire page to be styled however we want and include whatever HTML elements we want. This means that we could force any page to resemble the login page, but when the user submits the credentials, the submission is sent to us instead of to the intended server. The redirection of the credentials is done by replacing the location of the form posts to our Kali IP. To make the page as convincing as possible, we would ideally use an existing login page, replicate it, and change the action attribute of the form. The search application in the XSS sandbox has a login page located at login. While we could extract the HTML from this page and create a XSS payload to replace the content, we could also use JavaScript to get the HTML for us. That way, we don't have to handle massive amounts of HTML code in our JavaScript payload. If we inspect the form in the Firefox Developer Tools, we find that the current form posts to index.php within the login path. In our script, we'll have to change the action attribute to our Kali IP. We'll also change the method to get. This instructs the victim's browser to automatically add the payload to the URL query instead of the body, which makes it easier for us to find in our HTTP server logs. We'll first use fetch to grab the login page. Fetch responds with a JavaScript promise, and we can access the response by using the then method. By passing in an arrow function, we can get access to the text function within the response object. The text function provides us access to the input stream, in this case the HTML content of the login page. It also returns a promise. We can access the HTML content by passing another arrow function where the HTML content will be stored in a variable called data. To summarize, we make an HTTP GET request to login, extract the text from the response, and store the text within a variable called data. Next, we can replace the entire HTML document of the page we are running the XSS payload on with the data from the login page. We do this by searching for the HTML element and replacing the inner HTML with the HTML of the login page. Finally, we query for the newly created form and replace the action and method. We'll save the contents of this to our XSS file and start the HTTP server. Next, we'll go back to the web root of the search application and type in our payload to exploit the injection vulnerability. Finally, we'll render the exploit page on the victim's browser. Before we click Render, we'll also check the Blindly Enter Credentials setting. This will simulate a gullible user that will log in when prompted. The user will type in their password and submit the form. If we check our HTTP logs, we can find the value of the victim's username and password. Nice! We were able to extract the user's credentials. Case study: Shopizer reflected XSS. Let's analyze a reflected server-side cross-site scripting vulnerability that was found in Shopizer, an open-source e-commerce platform written in Java. The XSS vulnerability occurs in an unauthenticated section of the application. However, we will eventually target functionality that requires an authenticated user. We'll create our own account to test the application and play the role of the victim. We will attempt to discover the vulnerability for ourselves and then craft a payload that can target other users of the application. Before continuing, let's start Burp Suite. Turn off Intercept if it is enabled, and open the embedded browser by clicking the Open Browser button within this tab. Getting started. Let's browse to the shop page and begin by creating an account. We can start the registration flow by clicking on My Account, then Register. We'll fill out the form and click Create an Account. This will redirect us to our dashboard. With our account created, we can now click Home and start our search for a cross-site scripting vulnerability. Before continuing to the next section, please make sure to create an account. Discovering the vulnerability. Let's start exploring the application from the home page. We'll click on Products, then Handbags. Once the page loads, we'll notice something interesting about the URL. The highlighted value seems strange. It's sort of like a query string parameter, but there's no question mark indicating the start of the query string. Let's determine if the ref value is treated like a parameter. We'll inspect the HTML page source in our browser by right-clicking and selecting View Page Source. Once the new tab opens, let's open the browser's Find tool by pressing Ctrl F and then entering C:2. Stepping through the results, we find that it's used in several link URLs. More importantly, an inline JavaScript function that starts on line 721 uses the value. Line 729 contains the full value. If we modify this value in the URL and the application writes it to the JavaScript code, we might be able to inject our own JavaScript. Let's try using a canary to check if the application writes it in the JavaScript function. Any value will work, but we'll pick one that is unlikely to occur in the application so we have fewer results to search through. In this case, we'll place the literal string canary after C:2, so our URL ends with the updated value. Let's reload this page, then check the source. Interestingly, when we search for canary, we only get 3 results. The function loadCategoryProducts starting on line 721 includes one of the results. It seems we have some ability to inject content into the JavaScript code, albeit as a string value. Our next step is to try injecting a single quote to escape out of the string and determine if we can inject into the code itself. Let's place a single quote before canary. Refresh the page and check for it. The application wrote our canary in the JavaScript code, but we've broken the page. Our payload left the line of JavaScript with an extraneous single quote. Additionally, canary by itself isn't valid JavaScript syntax. If we check the JavaScript console in the browser, we'll find the following error. Let's update our payload to contain valid JavaScript after the single quote. We'll try an alert window. We'll close out the string, followed by a semicolon to complete the statement. We can place our alert last. Let's submit this value. If it works, we should get an alert box after the page loads. Unfortunately, that didn't work. Some application servers and firewalls will block a semicolon in a URL. Without access to the log files for the application or the server, we don't know where the issue occurred. We'll need to find another way to make our payload result in valid JavaScript. Let's try using plus signs instead of semicolons. Excellent! An alert box isn't very impressive, but we have confirmed we can inject arbitrary JavaScript code and the application will return it to our browser. In the next section, we'll craft a payload to load an external script from our Kali machine. This will let us deliver a more complicated payload to exploit this vulnerability and target other users of the application. Loading remote scripts. In the previous section, we were able to exploit a reflected cross-site scripting vulnerability by displaying an alert box using an inline payload in the URL. While this worked for that payload, our payload will grow in size if we want to perform more complicated actions. Let's try to use the XSS vulnerability to inject a link to an external JavaScript file. Such an external file wouldn't have the same size restrictions as a payload delivered in the URL. We have a few ways we can try to inject a script. We could close out the existing script block and try to inject a new script tag. Since we're injecting our JavaScript payload through the URL in this application, we might run into issues with restricted characters if we try to include a script tag. Fortunately, there are other ways to load additional JavaScript files into an application. Let's inspect the Shopizer application and determine what JavaScript libraries it uses. If the application loads JavaScript libraries, we might be able to use some existing functions to make a smaller payload. We can use the Sitemap tool in Burp Suite to find this information. Let's access the Sitemap tool by clicking on Target, then Sitemap. We can find the JavaScript files Shopizer uses by clicking on Shopizer, then Resources, then JS. The Shopizer application loads several jQuery files. The jQuery library makes DOM manipulation easier in JavaScript with helper functions. One of the helper functions we're interested in is the jQuery getScript function to load and execute a remote JavaScript file. While we can do this in vanilla JavaScript, using jQuery will save us a decent amount of space and simplify the payload. As a reminder, our previous payload injected JavaScript as part of the ref value in the URL. We'll create a new payload using the jQuery getScript function to load a JavaScript file from our Kali machine. First, let's create the JavaScript file to be hosted. We'll also start Python's HTTP server to serve the file on port 80. Next, let's craft the XSS payload that will load this file. We need to pass the jQuery getScript function a URL. We've already discovered that a semicolon causes issues with the payload, and ideally, we want to use the least amount of special characters as possible. We want to encode the whole payload in such a way that it is meaningless while the application server is processing the URL. The ideal encoding scheme would output alphanumeric characters that wouldn't impact the URL, such as no forward slashes. Considering these factors, we'll base64 encode the core of our payload and then include a function to decode it. We can use the decoder tool in Burp Suite to base64 encode our fetch call. Let's click on the Decoder tab and paste our payload in the text box. Since we'll be base64 encoding for this part of the payload, we'll click Encode As, then base64. Now that we have our payload base64 encoded, we need to wrap it in two function calls. Our first function will decode the value and return a string of our payload. We'll pass the string into eval to execute the string as JavaScript. As we found when we were displaying an alert, we'll also need to surround our payload in plus signs and quotes. Here's our final payload, including single quotes and plus signs. Let's submit this payload to the application. We will most likely receive an error. If the error isn't the first message displayed, it might be the second after our alert is dismissed. This error message causes a problem. Sometimes our payload is executed first, but other times the error is displayed first. When an alert is displayed, execution is paused and our payload might not be executed until the user dismisses it. Let's investigate the JavaScript console to determine what might have gone wrong. Let's reload the page again in order to generate the link in the console. The JavaScript console shows that the page tried to send a request but received a 400 error. Let's click on the link. This will redirect us to the Network tab, and if we click on the request, we can find the response from the server. We'll notice the server describes an invalid character found in the request target. This is most likely because of the value returned by the getScript function. We can fix this by base64 encoding the entire response using the B2A function. We'll have to wrap the entire eval in this function. When we send this payload, the page loads with no errors. Excellent! It seems our external JavaScript file was loaded. Let's click OK to close the dialog window. While this proof of concept included a simple script, the important concept is that we injected an external JavaScript file. Now that we've done that, let's work on a more complicated payload. Exploiting reflected XSS. Let's assess what we know about the application and what we might be able to do with cross-site scripting. The application uses a JSessionID cookie to track user sessions, but the cookie has the HTTP-only attribute set. Because the browser will block JavaScript from accessing the JSessionID cookie, we won't be able to steal another user's cookie with XSS. That being said, the browser will allow JavaScript to send requests that include the cookie as long as the cookie is scoped to the requested domain. Perhaps we can inject JavaScript code that will target functionality within the application. Let's explore the application as an authenticated user so we can familiarize ourselves with the functionality that is available. Let's sign in using the previously created victim account and click on Welcome, then My Account. There aren't a lot of options here. The Change Password functionality requires the user's current password, so we wouldn't be able to change a victim's password. However, we may be able to change their shipping address. Let's click on Billing and Shipping Information and then click on Add a New Address. Let's fill out the form with some placeholder values and submit it by clicking the Change Address button so we have a sample request. We should be able to send a post request like this using fetch or XML HTTP request. However, there is a catch. The post includes a customer ID parameter, which we might need to extract from the victim user. Before we investigate how to do that, let's first use Repeater to send this post with the customer ID value empty and review the response. We'll also replace the first name value with a new value so we can verify if the update worked. Excellent. We received an HTTP 200 response that includes the updated first name value. We won't have to worry about knowing the customer ID value after all. Our next step is to craft a JavaScript payload to send a similar request. We'll use the fetch function to send the request and pass it the URL and an object containing the various configurations necessary for the request. We'll start the options object by setting the method to post. Since our payload will effectively be hosted on the same domain as the application, we'll set the mode and credentials values to same origin. This should allow the browser to send the JSessionID cookie since the request will not be cross-origin. We'll include a content type header with a highlighted value. Finally, we'll include the post body contents with some proof of concept values. Now that we have our payload, we'll save it and start the HTTP server. Let's test this payload out on our own account. Let's first browse to the customer dashboard to make sure our session is still valid. If it's not, we'll need to log in again. Next, let's visit the handbags section and load our exploit URL, which will load the malicious JavaScript file from our Kali machine. We will paste our payload, then press Enter. The web page does not include any indication of whether our payload worked. If we check the HTTP History tab in Burp Suite, we should find that our post request was sent. We can verify the changes were saved by returning to the My Account page and clicking Billing and Shipping Information. Excellent. We were able to modify our user's shipping address with the reflected XSS vulnerability. While we wouldn't be able to review what is rendered in the victim's browser in a normal circumstance, we could exfiltrate this page from the user's browser using fetch as well. Same origin policy. An origin is the combination of a protocol, host name, and port number. Browsers enforce a same origin policy to prevent one origin from accessing resources on a different origin. SOP allows images, iframes, and other resources to be loaded onto the page, while blocking the JavaScript engine from accessing the contents of a response. We can test this behavior in the Sandbox application. Let's use Burp Suite's embedded browser so that we can review the HTTP requests that the web page generates. This application uses the Fetch API to send GET requests to a URL that we specify. We can also dynamically insert images into the page. We'll start exploring cross-origin requests by using the application to send a request to megacorp1.com. We'll enter the URL in the application and click Send Request. Our request failed. Let's check the browser's console for more information. We will open the developer tools with Ctrl-Shift-I and then click on Console. Since the target domain does not have a CORS policy, the browser blocks JavaScript from accessing the response. However, if we check the HTTP History tab in Burp Suite, we will find that our browser did send the request and it received a response. It's important to remember that SOP blocks JavaScript from accessing a response, but it does not block the outgoing request. Let's try to load an image. We previously mentioned that SOP allows images to be loaded cross-origin. However, it is important to note that this is allowed for image tags within HTML. If we attempt to load an image cross-domain with JavaScript, SOP should block JavaScript from accessing the response. We will enter a URL with an image in the URL field and again click Send Request. We received the same error message. But what happens if we use the URL in an image tag? Let's close the developer tools and then click Embed Image. The page embedded the image in the HTML and our browser loaded and displayed it. The important distinction in this case is that SOP blocks JavaScript from accessing the response of a cross-origin request, but the request is still sent. In some instances, simply sending a request can be enough to trigger some sort of state change in a web application. In most applications, requests that perform an action require authentication. Case Study: Apache OF-Biz. In this learning unit, we'll examine a CSRF vulnerability in Apache OF-Biz, an open-source ERP application. Apache OF-Biz Discovery. We'll start by clearing our burp history, and launch its embedded browser again. Next, we'll access the login page of OF-Biz. We'll enter our credentials and click Login. Before we continue exploring the application, let's inspect the server response for our login request. We can find the request and response for our login request on the HTTP History tab. The response to our login request contains 2 cookies, neither of which seem to be CSRF tokens. We'll also notice the cookies do not have the same site attribute set. One area that can be effective to target with CSRF attacks is user creation. If we can trick an admin user into executing our payload, we can create new users, potentially with elevated permissions or roles. Let's figure out how to create new users in OF-Biz. We'll start by clicking on Security. Next, we'll click on Create New. We'll submit this form with some simple data in it. Let's use test for the username and password for the password, then click Save to submit the form. Let's examine the post request in Burp Suite. The post body contains a few parameters that were not visible on the web page, but none of them contain anything that resembles a CSRF token. There are no additional headers beyond what Chromium has added. We should be able to craft a CSRF payload that will create a new user. Before we do that, let's figure out how to add a user to a security group. Let's click on Find Security Group. The resulting page lists out the various security roles in the application. After reading through the descriptions and clicking Next twice, we find the Super role. Based on its description, we will target this role. The options available to us in this section of the application change based on what we last clicked on. Let's click on Super to get options for security groups. We are presented with several new buttons. Next, we'll click on the New User Logins button. Let's add our test user in the User Login ID field and then click Add. Our test user has now been added to the Super group. Let's inspect the post request that we just sent to the web application. The post body and headers don't contain anything that resembles a CSRF token, so we should be able to exploit this functionality as well. We will exploit what we have discovered next. Apache OF-Biz Exploitation. We will need to build a small HTML page to exploit the CSRF vulnerabilities in this application. Let's create a file in the web root so that later on we can use Apache to serve the page. We'll start with the basic structure of a form element and use JavaScript to submit the form on page load. Now that we have the basic structure, let's add the input elements. The post request that our page generates needs to match the baseline request from the web application. We will need to add input elements, one for each key value pair in the original request, inside the form element. While we won't be going into all the specifics of creating a realistic phishing page, we will use hidden input fields to disguise our form. Our page will appear blank when opened in a browser. Let's test our CSRF page. First, let's make sure we have Apache running on our Kali VM. We'll also need to make sure our session in OF-Biz is still active, so let's log off and log back in. Next, we'll open a new tab in our browser and browse to our CSRF page in the new tab. Since our form auto-submits, our browser will be redirected to the last page we visited. The application created our new user. Let's review the flow in Burp Suite as well to make sure we understand what just occurred. After loading our CSRF payload page, our browser sent a post request to the OF-Biz application. The origin and referrer headers on our request indicate that the request originated from localhost. Our session cookie was included on the request. The server processed the request and created our new user. We need a second post request to add the new user to a security group. To achieve this, we could try to fish a user to a second exploit page. Alternatively, we could generate one page that uses two forms to make post requests. However, this setup could cause problems. We can use JavaScript to submit the forms, but the timing of the post requests is important. We need the application to process our first request to create the user before we can add the user to a group. Let's copy our existing HTML page into a new file. We'll start by adding a new form within the HTML body after our existing form. This form will handle adding our user to the supergroup. Since we'll be attempting to submit 2 forms, we'll set the target of both forms to blank so the browser opens the results in new tabs. We'll need to add this to the original form as well. Next, we'll create a JavaScript function to submit the forms. We'll need to add a head element to contain our script, and update the body tag's onload event to call the new JavaScript function. Let's remove the extra element. This approach is problematic. Some JavaScript calls can be asynchronous, meaning that the forms might be submitted essentially at the same time. If the server processes the second form request first, it will fail since the first form contains our new user. This might occur if the target user's internet connection isn't stable. We will revise this attack later on. For now, let's try it as is. We'll need to make sure our session in OFBiz is still active before loading our new CSRF page in a new tab. Our payload opened 2 new tabs, the second of which is on the Edit User Login Security Groups page. It seems our attack worked, but we can verify it by logging out of our current session and then logging in using the newly created account. We'll click on the portrait in the upper right-hand corner and then click Log Out. On the resulting page, we'll click Login to return to the login page and submit the credentials for the account we created with the CSRF attack. Excellent. Our attack worked, but our payload is a little noisy as it opened multiple pages. We may have been lucky on the timing of the requests, so we will revise our attack to be more reliable in the next section. Revising the CSRF payload. Rather than use 2 forms, let's use JavaScript to make the request directly without navigating the browser away from our payload page. We'll start with the basic structure and some common variables. Our file starts by declaring several variables within the script block. Using variables in this way allows the exploit to be more modular and easier to update. Next, we'll create 2 functions within the script tags. The first function will send the request to create a new user. The second function will send the request to add the new user to the super security group. Finally, we'll explicitly call our first function at the end of the script block so that a browser will execute our code when it loads the page. We're using the Fetch API to send our post requests in the No Cores mode. This restricts us to using a specific content type, which should be fine since the baseline request used that value. We'll set credentials to include to instruct the browser to send cookies on the request. Despite this setting, there are situations in which the browser might not send cookies on a request, depending on the core setting of the requested domain and the same site attribute of any cookie. We'll explore cores later on in this topic. Once again, we'll need to have an active session in OFBiz before loading our CSRF page. Let's check in Burp Suite to determine if our JavaScript worked and made our browser send the requests. It seems that our browser did not include any cookies on the request. Let's check our browser's console for any errors. Some messages were moved to the Issues panel. Let's click on Issues to collect more information, and then click on the Disclosure widgets to expand the details and affected cookies. Our browser did not send the cookies because they do not have the same site attribute set. Chromium defaults cookies without this attribute to lacks, which prevents the cookies from being sent in cross-site contexts. Let's review what cookies are set by OFBiz. We can check our most recent failed CSRF attack since cookies are set on the response. OFBiz uses the JSessionID cookie to track user sessions. The cookie is set without specifying the same site attribute. Let's test how our attack works if we manually set same site to none in our browser developer tools. We'll need to switch to the tab with OFBiz loaded and open developer tools again. This next step will be easier if we move the developer tools to the bottom of our browser window. Next, we'll access the cookies set by the OFBiz application. To set the same site attribute on our cookie, we need to double-click in the same site column, type none, and press enter to save the change. We can now return to the browser tab with our CSRF page open and refresh it. Let's check Burp Suite to determine if our browser sent the cookie this time. The browser included the session cookie on the requests, and our attack was successful. Let's change the JSessionID's same site attribute to lacks. Reload our CSRF page, and check Burp Suite. As with our initial attempt, the browser did not send the session cookie. This example demonstrates how effective the same site attribute is at preventing CSRF attacks. Exploiting weak CORS policies. Due to CORS' very nature, websites that enable it can leave themselves and their users open to CSRF-style attacks if there are any weaknesses or misconfigurations in the site's CORS settings. We will return to our sandbox application to examine these misconfigurations and the potential attacks they open up. Weak CORS policies. Discovery. Let's use Burp's embedded browser. Next, we will access the CORS functionality of the practice application. In addition to supporting CORS, this application allows us to configure the HTTP-only, secure, and same-site attributes of the session cookie. For now, we will select None for same-site and True for secure and HTTP-only before clicking Get Cookie. We can use Burp Suite to verify the cookie was set according to the attributes we selected. Next, we'll click on Get Code. When we inspect the response in Burp Suite, we find there are two CORS headers. The presence of access control headers indicates this application supports CORS at some level. Let's use Repeater to test the application further. We'll right-click on the GET request and select Send to Repeater. Next, let's click on the Repeater tab and then click Send to send the request to the server. We now have a baseline request and response that we can use for additional testing. Our next step will be to determine what origins the application trusts. Trusting any origin. We know the application supports CORS. Let's determine if we can access the secret code from an external domain. If we send a GET request to code without a valid session cookie, we get a response with an error status. Since we need to be authenticated to get the code, we need to send a valid session cookie on the request. A browser will not include credentials on a CORS request if it's missing the Allow Credentials header. Additionally, the Allow Origin header being set to a wildcard would overrule the Allow Credentials header, even if it was set. Our original request did not include an origin header. Let's try adding one and reviewing how the application responds. We'll click Go Back in Repeater until we find our baseline request. We'll add an origin header set to Hello CORS on the request and then click Send. The response includes the origin value we set and Allow Credentials set to True. This may seem odd initially, but there are valid reasons why a developer might want to allow multiple domains to access its resources in an authenticated manner. Remember, a wildcard value for the Allow Origin header doesn't permit Allow Credentials to be true. If developers want their application to support multiple origin values, they must create unique solutions. Instead of responding with a wildcard, they could just respond with whatever the value of the origin is in the request. We should be able to call the code endpoint from an external domain. We will need to create an HTML page on our Kali host. The JavaScript function in this page uses the Fetch API to send a GET request to the code endpoint using CORS mode and including credentials. The function then logs the JSON body of the CORS request to the console. After making sure Apache is running, let's visit the CORS page in a new tab in our browser. We need to have a valid session cookie to the practice application in a separate tab. There's no immediate feedback on our CORS exploit, so let's check the browser console. This example proves that JavaScript running on a different domain can access the results of a CORS request. In a real-world scenario, we wouldn't be able to inspect the victim's browser console. However, since JavaScript can access the response, we can update our page to send the secret code to an arbitrary domain. Let's create a copy of our HTML page. We'll update the function to send the result back to our Kali VM. We've included a fetch call with the JSON body in the query string. We are using json.stringify to convert the JSON response to a string, then calling the encode URI component function to encode any characters that might cause the URL to be invalid. Let's test the page by accessing it in our browser. Again, the page provides no indication of what happened. Let's check our access log for Apache. Excellent. Our CORS page sent a request to get the code on behalf of the victim user, then sent the code to our Kali machine. While we played the role of the attacker and the victim, this example illustrates how to exploit permissive CORS settings to steal data from users. In real-world applications, attackers can exploit CORS to steal sensitive data, such as private messages or bank account numbers. They can also exploit CORS to perform actions as the user, such as transferring money or changing a password to completely compromise the victim's account. Improper domain allow list. The allow origin header can only set a single domain. When an application needs to support CORS with multiple origins, the application must include server-side logic to respond with the appropriate value. Applications usually need to inspect the origin header on a request to determine if it matches one of the allowed domains, and then add the appropriate value in the allow origin header on the subsequent response. If the application contains logic errors in this functionality, it can introduce misconfigurations in the CORS policy. Two common approaches that result in these misconfigurations are checking if the origin header on a request includes a preset value or ends with a preset value, and then reflecting that header value. Our practice application includes an additional endpoint with flawed allow list functionality. Let's use curl to send a request to the endpoint. We'll use -x to send an options request, -i to include headers on the output, -k to allow insecure server connections when using SSL, and finally, the URL. We didn't specify an origin header on our request, but the server responded with an allow origin header. Perhaps that is the only allowed origin. However, let's try sending a request with an origin header that includes a modification of that value. We'll use curl again and use -h to add an origin header. The server responded with an allow origin value that matches the value we submitted, but we only changed the protocol and subdomain. Let's try modifying the end of it, too. The server responded with the original allow origin value. It seems that changing the top-level domain caused the server to respond with the default value. We were able to append a subdomain, but we'll keep in mind the default does not include a subdomain. What will happen if we alter the domain name by prepending something to change the domain name? Let's use curl again, changing the value of the origin header. The server used the origin value we sent and set it in the allow origin header. The application seems to be allowing domains that end with offensive-security.com, perhaps to allow for various subdomains. However, since it is not checking for a leading period, we can alter the domain name to something entirely different as long as it ends with offensive-security.com. This type of misconfiguration can be more difficult to exploit as it relies on obtaining a specific domain to conduct the attack. However, crafting an HTML page and JavaScript to deliver a payload to exploit this misconfiguration functions essentially the same way we covered earlier. Basic SQL syntax. While there is a standard syntax for SQL, most database software packages are implemented with some variations. However, the basics are generally the same. Let's cover some basic SQL concepts and syntax to develop more familiarity with it before moving on to exploitation. A relational database consists of one or more tables, each of which includes one or more columns. Each entry in a table is called a row or record. The easiest way to conceptualize a table is to actually interact with one. Let's use our sandbox application to access the SQL console. We'll start with a simple query. Queries are instructions to the database engine that we can use to retrieve or manipulate data in the database. A select query retrieves data from one or more tables in a database. Let's begin with this basic interaction. When we write a select query, we need to specify what data we want and where we want it from. The what is formatted as a list of one or more columns. We can also use an asterisk as a wildcard to query for all columns in a table. The where indicates which tables we want to use. We'll start with a basic example that selects data from one table. We can paraphrase this query as retrieve all columns and records in the menu table. Let's run this query in the query field. The result shows the columns ID, name, description, and price. We'll observe 3 rows of data for 3 listed items. In addition to retrieving all records from a table, we could also introduce a conditional clause to our query by using a where clause. A where clause requires one or more columns and a conditional statement for each column. We can paraphrase this as retrieve all columns from the menu table, showing only records with an ID of 10. These are just some of the basics. We can also insert, update, and delete data in tables. Rather than covering those statements here, we'll explore additional SQL syntax as needed as we learn different SQL injection techniques. MySQL specific functions and tables. While the following commands are specific to MySQL, many of them will also work on MariaDB, an open source fork of MySQL. We can use the version function to retrieve the version of a MySQL database. We can obtain the user account currently connected to a MySQL database with the current user function. We should keep in mind that this is a user account for the database and does not necessarily correspond to an OS-level user. MySQL segments tables into different databases, synonymous with schemas. Databases can be user-defined. However, MySQL stores information about itself in the information schema database. If we are able to execute arbitrary SQL, we can retrieve the names of the databases by using show databases. For cases in which we need to extract information with a select statement, we can query the tables table in the information schema. In this example, we included a group by clause to return only one record for each unique value in the table schema column. We can query the same table to retrieve a list of the tables in a specific database. If we can execute arbitrary SQL, we can obtain the same information with show tables. However, this command will only list the tables in the current schema or database. The columns table in the information schema contains information about the columns of all tables in the database. We can query this table to learn more about an unknown database. Although this section is by no means exhaustive, it serves as a foundation for enumerating unknown MySQL and MariaDB databases. Microsoft SQL Server specific functions and tables. We can obtain the version of a SQL Server we need by selecting Version. We can obtain the name of the user account currently connected to the database by selecting System User. As with MySQL, this user is specific to the database and may not be a system-level user. While it can be renamed or disabled, SA is the default name for an administrator-level account in SQL Server. If we can exploit SQL injection with a query run by the SA account, we will typically receive full access to all functionality with SQL Server, meaning we should be able to completely compromise it. We can obtain a list of databases from the Databases table in the System Catalog, abbreviated as SYS in queries. The System Catalog contains metadata about the database. We can obtain a list of table names within a database by querying the Tables table in the corresponding information schema. Once we know a table's name, we can query the Columns table in the information schema to obtain its column names. This section is by no means exhaustive, but provides the basic details needed for enumerating unknown Microsoft SQL Server databases. PostgreSQL-specific functions and tables. We'll now focus on enumerating PostgreSQL databases, which use similar syntax to MySQL. We can obtain the version of a PostgreSQL database with the version function. We can obtain the user account currently connected to a PostgreSQL database by selecting Current User. We do not include parentheses in this case. The user account for the database will be returned, which does not necessarily correspond to an OS-level user. PostgreSQL can segment tables into different databases, which are synonymous with schemas. PostgreSQL stores information about itself in several tables, beginning with PG. We can query the PG database table for the names of the logical databases on the server. PostgreSQL databases also contain an information schema that can be queried for information about the database server. We can query this table to learn more about an unknown database. The Tables table includes a row for every table in the database, including the PG tables. We can query for only user-created tables by including a where clause. Once we have identified the tables in a database, we'll next want to identify the column names for the tables we're interested in. The columns table in the information schema contains information about the columns of all tables in the database. Although it is not exhaustive, this section provides a foundation for enumerating unknown PostgreSQL databases. Oracle-specific tables. Of the database software we're reviewing in this topic, Oracle DB is perhaps the most different from the others. It uses the same SQL syntax for basic queries, but there are many idiosyncrasies we need to manage when working with functions or data about the database itself. First, we'll need to obtain the Oracle database version. Because we're executing these queries in the SQL console, we don't include a semicolon at the end of the query. We can obtain the user account currently connected to an Oracle database by selecting the user function. However, Oracle databases require a from clause with any select statement. Oracle databases always include a table named dual. This table has one column named dummy and one row with value X. When working with an Oracle database and we need to select static values or data from functions, we can include from dual to create a syntactically valid query. As with the other databases we have reviewed, this function will return the user account for the database, which does not necessarily correspond to an OS-level user. Oracle databases create a schema for each user. In this context, a schema is essentially a set of tables, views, and other database objects. Each schema carries its own set of permissions that can enable users to access data in other schemas. Since the database creates a schema for each user, we can obtain a list of schemas by querying for the users in the All Tables table. By including Group by Owner in our query, we'll limit our results to a distinct list of user names. This table contains a row for every table in the database. We can query the table name column on this table with a where clause to retrieve the tables in a particular schema. Oracle databases include many system tables with a $sign in their name. However, there is nothing preventing a user from creating their own table with a $sign in the table's name. This means we can safely assume that all system tables include a $sign, but not all tables with a $sign are system tables. After identifying the tables in a schema, we'll want to identify the column names for the tables we're interested in. The All Tab Columns table contains information about the columns of all tables in the database. We can query this table to learn more about an unknown database. The more we know about the column names and data types of the table we're attempting to extract, the easier exfiltration will be. This section is by no means exhaustive, but it offers foundational information needed to enumerate unknown Oracle databases. Sorting. Keywords such as sort, order, ascending, and descending are often used as parameters in a SQL query to sort results. If we can manipulate the values of these parameters, we might be able to inject our own SQL into the query. Let's try crafting a query using some of these values to get more comfortable with their use. We'll return to the SQL console in our sandbox application. Let's try sorting via the simple select statement. We'll use the keywords order by followed by the column we wish to sort by. We could also include ASC or DESC to specify ascending or descending, respectively. Most databases will default to ascending order if a query includes an order by clause without specifying ascending or descending. Let's try sorting by entering select name, price from menu order by name in the query field and clicking submit query. Depending on the application, we might be able to inject into the column name or the order. Instead of ordering by a column name, we can also specify a numeric value corresponding to one of the returned columns. For example, if we submitted the query select name price from menu order by 2, the database would sort the results based on the price column. If we specify an invalid column, the database could throw an error, hinting at the existence of a SQL injection vulnerability. We can also use this technique to enumerate the number of columns in a query, iterating the value until an error is thrown. Boundary testing. Boundary testing is a common software testing technique that we can also use to find SQL injection vulnerabilities. Essentially, when we encounter a parameter that appears to take a limited dataset, we should submit values that fall outside that set to determine how the application responds. Let's try boundary testing in the SQL console in our sandbox application. We'll enter select from menu order by 4 descending as our query, leave the database value set to MySQL, and click Submit Query. Let's suppose we encountered an application allowing us to control the input used in the order by clause. Essentially, this means we could change the 4 to something else. Since the application displays 4 columns of data, we would want to submit a value larger than 4. One approach we might take is to make several requests, incrementing the value each time until we receive an error or a non-standard response, such as no results being displayed. Let's update our query to select from menu order by 5 descending and click Submit Query. The application responded with an error message in this case, indicating the menu table has 4 columns. Even if the application did not respond with a verbose error, we could still infer this information after submitting an invalid column number based on the size or content of the response. This can be a useful technique for identifying potential SQL injection vulnerabilities and enumerating the number of columns selected in a query. Fuzzing. We can use fuzzing as an effective technique for identifying potential SQL injection vulnerabilities. We may not successfully exploit more than a basic query vulnerable to SQL injection, but we can nevertheless inspect how an application responds to fuzzing to identify endpoints that respond differently based on our payloads. We can then perform manual testing to validate any potential findings. Let's try it out using wfuzz against our SQL Sandbox application. We need an example request from the application, so we'll start Burp Suite and open the embedded Chromium browser. Next, we will navigate to the SQL Sandbox application and click on Introduction. We'll enter 5 in the Menu Item ID field, leave the Database field set to MySQL, and then click Submit Query. We don't care about the response in browser. Instead, let's check our HTTP history in Burp Suite. We will find a post request to API intro. Now that we have a baseline request in Burp Suite, we can copy the post body for use with wfuzz. We'll set -C to enable output with colors, and set our payload list with -Z, using one of wfuzz's word lists tailored to SQL injection. Next, we'll specify our post data with -D and update the value of the name parameter to fuzz, so wfuzz will place payloads in that parameter. Finally, we can set the target URL with -U. These results require some interpretation. One useful approach is to check the response code and response size. For example, a 200 response code with a 2-character response is likely an empty response. Alternatively, a 200 response with a size greater than 2 characters might be a valid payload. A 500 response with a size greater than 2 characters, for example, might contain a useful error message. We'll need to send a few payloads using Repeater to more closely inspect these responses. Let's start with the following payload, omitting the double quotes. As we suspected, the response includes an error message. The application created an invalid SQL query after processing our payload. The error message also includes the SQL query. We could use this error message to craft a better payload, but for now, let's check one of the payloads that generated a 200 response with a size greater than 2. We'll try updating the ID field to 0 or 1 equals 1, replacing the spaces with plus signs to URL encode the string, then click Send. The server responded with multiple items. It seems that this payload was able to exploit the SQL injection to return the entire contents of the database table. Based on the error message, we know the SQL statement we're injecting into is select ID, name, description, price from menu where ID equals. The payload we tested therefore completes the SQL statement to select ID, name, description, price from menu where ID equals 0 or 1 equals 1. The where clause now contains two conditions with an or operator, meaning any record that matches either condition will be returned. The database will process 1 equals 1 as a true Boolean value and return every row in the menu table. We could use this payload as a building block to craft a more specialized payload. Fuzzing will not always identify a payload exploiting SQL injection vulnerabilities, but it is a useful technique for testing and identifying endpoints that might be vulnerable. Error-based payloads. As we begin working towards exploitation, we'll use any error messages we uncover to learn more about the database, beginning with the database software version. Once we know this, we can refine our payloads and determine what we can do with the SQL injection vulnerability. If a web application discloses simple database error messages, we can inspect those messages for keywords or identifiers that leak details about the database software. If an application returns verbose errors, we may be able to extract data from partial query results. One way to do this is to force erroneous data type conversions. For example, most databases can convert a date field to a string or varchar field, but converting a string to a date will likely cause an error if the string value does not match the expected date format. Some databases will include the value that caused a conversion error in an error message. We can demonstrate this with PostgreSQL and SQL Server by selecting the database version and converting it to an integer. Let's try out this technique against SQL Sandbox Intro. We'll use the cast function to do the conversion. We'll enter cast version as integer in the menu item ID field. For the cast function, we're going to pass in the column or field we want to convert, followed by as and the data type we want to convert the field to. Let's select SQL Server as the database. Finally, we'll click Submit Query. The server responded with an error message that included the database version. This technique will also work on PostgreSQL databases, replacing the version to match the database-specific syntax. MySQL handles the cast function differently. The function will return a value, including null, instead of throwing an error. However, MySQL has two XML functions, extractValue and updateXML, that will return the value that causes an error. Let's try using the MySQL extractValue function. According to its documentation, it takes two parameters, an XML fragment and an XPath expression. We don't need to be XPath experts to use this function. In fact, we will intentionally misuse it by submitting an invalid XPath expression. We'll use the following payload. In this payload, we call the extractValue function and pass in a blank string as the first parameter. For the second parameter, we use the concat function to concatenate the greater than symbol and version. We can use many different values for the first value in the concat function, as long as the resulting value is not a valid XPath expression. We want to avoid values that start with a /, a period, the @ character, or a completely alphanumeric string, since these values would start a valid XPath expression. We are using the greater than symbol because it is a delimiter in XML and cannot be part of a valid XML node. Let's enter our payload in the menu item ID field, select MySQL in the database field, and click Submit Query. The server response includes an XPath syntax error with the MySQL database version. In a similar way, we can leverage XML functions in Oracle databases. However, the syntax is the most complicated we've used so far. Although we won't delve too deeply into the details of this vector, we'll walk through this useful payload. For demonstration purposes, this payload is formatted with line breaks and numbers. We'll begin with line 4 since it is a subquery that will be executed first. This subquery is selecting the first 30 characters with the substring function from the banner column in the first row of the version table. Next, we use the double pipe operator on lines 3 and 5 to concatenate the result of the subquery into a new select statement. On line 4, we've included the substring function because Oracle limits column names to 30 characters or less. When this line is executed, the result is a value like Oracle Database 11G Express Ed. Once concatenated with lines 3 and 5, the result will be select Oracle Database 11G Express Ed from sys dual. Line 2 calls the getXML function. This function accepts a SQL query, executes it, and converts it to XML. The results are passed to toChar, which converts the results to a character string. In this case, getXML will run the query, which contains an invalid column name. Let's try it out on intro. We'll enter the following query in the menu item ID field. We'll then select Oracle as the database and click Submit Query. The server responded with an error message that includes the substring as an invalid character. By adjusting the inner query and iterating the start and stop value of the substring function, we should be able to extract any value from the Oracle database. There are many more database-specific functions and error-based SQL injection vectors. We can search online to find more information about these vectors. Union-based payloads. In order to extract data from the database, we need to inject SQL code that will return the data we're interested in. One way we can do this is with the union keyword, which instructs the database to combine and return the results of two queries. By default, most database software will remove duplicate results when a union is used. We can avoid this behavior by specifying union all to include all rows without deduplication. Let's try writing a union query in our SQL console. We'll start with a basic select statement and append the union keyword followed by a second select statement. We'll target the users table even though it only has 3 columns. We could omit one column from the menu table, but normally we wouldn't have that much control over the SQL statement we're injecting into. Instead, we can select a static value. We'll enter our query, then select MySQL as the database and click Submit Query. The database returned the results of our union query and the application joined the results. When we exploit a SQL injection vulnerability by injecting a union, we want to make sure the data we're trying to extract will be rendered by the application in a way that we can access. Not all applications will display every column or field of data. Next, let's try using a union-based payload in a SQL injection attack. From our previous tests, we know we're injecting into the where clause. We'll enter a value to complete the where clause and then add our union payload to read from the users table again. Our payload was successful and we have gained access to data from the users table. In this example, the password is in clear text, but many databases will instead store passwords as hashes to prevent hackers from obtaining the clear text values of passwords. Let's review what SQL statement the application executed here, including our payload. We started our payload with a 0 to complete the comparison in the existing where clause. We followed that with the union all keywords before including an additional select statement. The query we are injecting into has 4 columns, so we needed to match the column by adding a 4th column with a static value, 0, that matched the data type of the corresponding column, price. While error-based payloads are generally database-specific, the union-based approach works for most database software as long as we know what tables to target. Union-based payloads are an excellent technique to enumerate the structure and contents of a database since they return data that is rendered by the application. Stacked queries. Some database software can execute more than one query at a time. These are known as stacked queries. While conceptually similar to a union, stacked queries are individual queries submitted at the same time and executed sequentially. We can try stacked queries in our SQL Sandbox application. We'll enter 10, select from users in the menu item ID field. Select PostgreSQL as the database and click Submit Query. The server responded with only the contents of the user's table. From a black box perspective, we cannot tell if the database executed the first query, but it doesn't matter for our purposes. We were able to inject a second query and view the results. However, we should note that this technique's usefulness depends on how the application handles results. If the application validated the column names in the results, for example, this approach could cause an application error. Another way we can potentially leverage stacked queries is to add, update, or delete data in a database. These types of queries do not return results when they are executed, so we will need another way to determine if the stacked query was executed. Let's try inserting a new user. Insert statements use the following syntax. Since we need to know the name of the table and its columns to insert data, proper enumeration of the target database is very important. Let's try using stacked queries in our Sandbox app. The application did not return any rows of data. Since the second query we stacked after the original query does not return any data, this may mean our insert statement was executed successfully. We can use the SQL console in the Sandbox application to directly query the users table to determine if our row was added. Excellent. The application executed the stacked query and added the new user record. We could have used another stacked query or a union-based payload to verify the record was added as well. While we used PostgreSQL for demonstration purposes, Microsoft SQL Server also supports stacked queries. Reading and writing files. Some database software include functions that can read files from or write files to the underlying server. We can use these functions to exfiltrate data from the server or write files, such as web shells, which we can use for additional attacks. PostgreSQL can read and write local files using the copy keyword. Specifically, we can use copy from to insert data into a table from a file, or copy to copy data to a file from a table. In order for copy to succeed, the user that owns the PostgreSQL server process must have access to the file being read or have write permissions to the directory where the file will be created. We can practice this in the Sandbox application. The first line of the payload will create a new table named temp with one column named data. The second line of the payload will copy the contents of Etsy password into the temp table. The last line selects all rows and columns from temp. Our payload worked, and we now have access to the contents of Etsy password. However, this approach requires that the database user executing the query can create tables, and the user running the database service has access to Etsy password. We can also use the PostgreSQL pg-read file function to read files. Unlike copy from, this function will not insert the results into a table, making it useful in situations in which the database user account we are exploiting cannot create tables. Note that the function returns a single field containing the full contents of the file. If we want to use this function in a union-based attack, we may need to include static values to match the number of columns in the original query. In MySQL, we can read files using the load file function. However, there is a catch. MySQL has a secure file priv system variable that restricts which directories can be used to read or write files. Some versions of MySQL do not set this variable by default, which means MySQL can potentially read or write any file subject to OS file permissions. Setting the value to an empty string is the same as leaving the value blank. Other versions or hardened configurations will set this variable to a specific directory. Let's check the value of this variable. Since secure file priv is enabled, set to a non-null value in our Sandbox application, we will be restricted to reading and writing files in var lib mysql files. This will prevent us from writing to the web root, but we can still practice writing and reading files. Since we don't know what files will be in the writable directory, we'll first write a file there and then read it. We can write a file with a select statement ending with into outfile file. The file location must be writable to the OS user the database software is running as. These different levels of permissions can be somewhat complicated, resulting in some database administrators opening permissions on the directory. Such misconfigurations may work to our advantage in some situations. Let's try it out by writing the contents of the user table. Writing a file in this way does not return any results. We also did not receive an error, so we'll need to use another query to verify if the database created the file. Let's try using the load file function to read the file we just created. We can use the function with a select statement and pass in the file we want to read, including the full file path. We were able to read back the file we created. If we attempt to read a file outside of the permitted directory while secure file priv is enabled, the database will return a null value. Remote code execution. Some database software can directly call operating system commands. Usually, these features are either disabled by default or restricted to administrative users. If we are able to access one of these functions through SQL injection, we should be able to obtain remote code execution on the underlying server. In Microsoft SQL Server, the XP command shell function takes a string and passes it to a command shell for execution. The function returns any output as rows of text and is disabled by default. If the function is enabled, it must be called with the execute keyword instead of select. For this reason, we usually need the ability to exploit stacked queries to use the XP command shell in a SQL injection payload, unless we can specify the entire SQL command. If our database user has the appropriate permissions, we can enable XP command shell using these commands from Microsoft's documentation. Once XP command shell is enabled, we can call it using the following syntax. Note that the command is not enclosed by parentheses. The command is run in a shell with the same permissions as the SQL Server service account. While SQL Server is often run on Windows servers, it can also be run on Linux. However, the Linux version of SQL Server does not support several functions, including XP command shell. As with most attack techniques, we need to perform proper enumeration to understand our target before deciding on a specific SQL injection technique or payload.